So, let's go. The scariest thing about this list is that it was shorter last year. You know about solar storms? Big cloud of plasma launches off the sun, takes a day or two to cross 93 million miles, slams into Earth's magnetic field, and maybe knocks out some satellites. You've heard that story. You've got warning time. Satellites at the L. 1 point between Earth and the Sun give you 15 to 45 minutes minimum before impact. Solar proton events don't work like that. When certain solar flares erupt, they don't just throw plasma. They accelerate individual protons to near the speed of light. Not a cloud drifting toward you over hours. Individual particles screaming across the solar system at relativistic speed, and they arrive 8 to 15 minutes after the flare fires. Here's the problem. The light from the flare, the signal that tells us something happened, also travels at the speed of light, which means the warning and the weapon arrive at almost the same time. During a strong event, passengers on polar flight routes absorb the equivalent of several chest X-rays in a single trip. At high latitudes, radiation reaches ground level, not satellite-killing radiation. People-reaching radiation. A farmer standing in a field in northern Canada gets dosed before anyone on Earth has issued an alert because you can't warn faster than light, and these protons are keeping pace with it. Now scale it up. The tree ring record shows the sun has fired events hundreds of times stronger than anything in modern history. If one of those happens, 8 minutes is the entire window between normalcy and a radiation storm at ground level across every high-latitude country on the planet. No siren, no evacuation, the sky doesn't change color, you just start accumulating dose, standing wherever you were standing when it fired. And that's the fastest thing on this list, everything else is slower. Not necessarily gentler. This one isn't an explosion, it's a wound. Sometimes regions of the sun's magnetic field just open. Instead of looping back to the surface the way they should, the field lines point straight outward into space like an open door. And through that door, solar plasma pours out at 600 to over 1,000 kilometers per second. Normal solar wind moves at 3 to 400. This is double that or more. You can see them. In ultraviolet images, they're enormous dark patches on the sun's face. Some stretch over 500,000 kilometers across, and they don't close quickly. A coronal hole can persist for months, surviving multiple 27-day solar rotations. Every time the sun turns and points that hole at Earth, the stream hits again. Same wound, same bombardment, on a schedule. In September 2025, a butterfly-shaped coronal hole triggered strong geomagnetic storms. Auroras stretched down to Connecticut. In June 2025, a coronal hole stream arrived at the same time as a flare-driven plasma cloud, and the combination pushed solar wind to 1,000 kilometers per second and produced severe-level geomagnetic storms. That's the part nobody talks about. A coronal hole by itself is bad. A coronal hole plus a solar storm arriving at the same time is worse than either one alone, because the high-speed stream basically clears the road for the heavier hit behind it. Astronauts on the International Space Station know when the particle flux goes up. They close their eyes and see white flashes. Not a malfunction, not imagination. Charged particles punching through their skulls and detonating against their retinas. Cherenkov radiation inside your eyeball. The sun doesn't need to explode to hurt you. It just needs to stay broken. Number 3, the oh my god particle. October 15th, 1991. A detector in the Utah desert called the Fly's Eye picks up a single proton. One proton. One subatomic particle. Moving at 99.999999999999999999999999999999999%. The speed of light. The energy in that particle was roughly equivalent to a baseball thrown at 60 miles per hour, all of it compressed into something smaller than an atom. 40 million times more energy than the most powerful particle accelerator ever built by humans. They named it the oh my god particle because what else do you call that? Here's why it's disturbing. There's a speed limit for cosmic rays traveling across the universe. Above a certain energy, they should collide with photons left over from the Big Bang and lose speed over intergalactic distances. This particle was way above that limit, which means its source had to be relatively close in cosmic terms. So they looked in the direction it came from. Nothing. No galaxy, no black hole, no remnant of anything that could have produced it. Then, In 2021, a detector in Japan caught the second most energetic cosmic ray ever recorded. They named it Amaterasu, after the sun goddess. They traced its arrival direction. It pointed at a void, a region of the universe with essentially nothing in it. No known object, no known process, no known source. You are being hit by about 1 cosmic ray muon per square centimeter per minute right now. They pass through your body constantly. Most of them are harmless. But somewhere out there, something is accelerating single particles to energies that shouldn't exist, firing them from directions where nothing should be. And we built a detector the size of Rhode Island in Argentina just to catch roughly one of them per century. The universe has a gun. We don't know where it is. We don't know what built it. And it's pointed everywhere at once. 42,000 years ago, Earth's magnetic poles started to swap. North drifted south. South drifted north. The transition lasted about 800 years. But the swap itself wasn't the disaster. The disaster was the in-between. During the transition, Earth's magnetic field didn't just weaken. It dropped to somewhere between 0 and 6% of its current strength. Your magnetic shield, the thing standing between you, and the full blast of cosmic radiation, was functionally gone. Scientists named it the Adams Event, after Douglas Adams. Because it happened 42,000 years ago, and 42 is the answer to life, the universe, and everything in the Hitchhiker's Guide. Astrophysicists have a sense of humor. It's usually dark. We know what happened during this event in unusual detail because of a tree. In 2019, an ancient Kori tree was found preserved in New Zealand. It had been alive during the Adams event, and its rings recorded atmospheric radiocarbon levels year by year, giving scientists the first high-resolution timeline of what the collapse actually looked like from the ground. The ozone layer was likely shredded by increased cosmic radiation. Electrical storms raged. Auroras lit up the tropics, places that should never see them. Arctic air masses pushed south across North America. Now, here's where the science gets contested, and it's worth being honest about it. The Adams event coincides with the extinction of Neanderthals in Europe, the disappearance of Australian megafauna, and a sudden explosion of cave art, as if humans were driven underground by increased ultraviolet radiation at the surface. That's a compelling story. It's also debated. A rebuttal published in Science argues the timing is coincidental, and points out that earlier magnetic excursions happened without similar catastrophes. What isn't debated is this. Earth's magnetic field has weakened about 9% in the last 170 years. Magnetic north is racing toward Siberia at 55 kilometers per year. Whether that's the start of another excursion or just normal wandering, nobody can tell you for sure. But if it is, the last time it happened, we were living in caves. This time, we have 7,000 satellites, a global power grid, and 8 billion people whose survival depends on systems that didn't exist the last time the shield went down. You know what a supernova is. A star dies, it explodes, it outshines its entire galaxy for a few weeks. Dramatic, violent, well documented. A hypernova makes that look gentle. When a star bigger than 30 times the mass of our sun collapses, it doesn't just explode outward. The core caves in so fast it forms a spinning black hole, and that black hole launches twin jets of material at nearly the speed of light. Relativistic jets that drill straight through the dying star and ran out the other side. The energy output is at least 10 times greater than a standard supernova. The first one ever confirmed was spotted in 1998, 120 million light years away, burning 100 times brighter than it had any right to. In 2015, a simulation showed what happens in the first 10 milliseconds of collapse. The magnetic field amplifies to 1,000,000 billion times the strength of Earth's. 10 milliseconds. That's the jet engine igniting. But here's the part that should bother you. In 2023, astronomers detected the most energetic transient event ever observed. They nicknamed it Scary Barbie. At first they thought it was a hypernova. It wasn't. It was something else entirely. A massive gas cloud being ripped apart by a black hole. They didn't have a category for it. A few years before that, they detected the most energetic supernova ever recorded, 5 times more powerful than a typical hypernova. Didn't have a clean category for that either. Hypernovae happen about 5 times per million years per galaxy. The nearest candidate is Eta Carinae, 7,500 light-years away, a massive unstable star that erupted so dramatically in 1843 that it briefly became the second brightest star in the sky. Its jets aren't aimed at us. Probably. But jet orientation isn't always knowable in advance. The threat here isn't just hypernovae, it's that we keep discovering new categories of explosion. The catalog of ways a star can die was incomplete until a few years ago. Nobody can promise you it's complete now. There are roughly 1 billion neutron stars in the Milky Way. Most of them are invisible. A neutron star is what's left when a massive star explodes and the core doesn't quite become a black hole. Instead, it compresses into a ball about 20 kilometers across, the size of a city, with the mass of the entire sun. A teaspoon of the material weighs about 6 billion tons. That's roughly the combined weight of every human being on Earth in a volume smaller than a sugar cube. When these things are born, the explosion is rarely symmetrical. The asymmetry gives them a kick, a natal kick that sends them hurtling through the galaxy at hundreds of kilometers per second. The fastest one ever clocked was doing over 1,100 kilometers per second. That's fast enough to escape the Milky Way entirely. The young ones pulse. They spin. They emit beams of radiation. We can see them. But old neutron stars stop pulsing. They cool down. They go dark. A cold neutron star emits almost nothing detectable. It's just a city-sized object with the mass of a star, screaming through the galaxy in total darkness. We have no census of nearby ones. We can't see them. If one were headed toward the outer solar system right now, we likely wouldn't know until it started pulling things off course. Oort cloud objects scattered inward like billiard balls. Planetary orbits destabilized. Not by an explosion, not by radiation, just gravity from something we never saw coming. Right now, the solar system is inside a patch of warm, thin gas called the local interstellar cloud. It's about 30 light years across and will exit it in roughly 1900 years. Nobody knows what's on the other side. The heliosphere, the giant bubble of solar wind that wraps around the entire solar system and shields it from interstellar radiation, isn't a fixed structure. It's a pressure balance. Solar wind pushes out, interstellar gas pushes in. If the gas outside gets denser, the bubble shrinks. If it gets dense enough, the heliosphere can contract to inside Earth's orbit. You lose the shield entirely, not for a day, for as long as you're inside that dense region. This may have already happened. Around 2 to 3 million years ago, isotopes that don't form on Earth, iron-60 and plutonium-244, spiked simultaneously in deep ocean sediments, Antarctic snow, and lunar soil. All from the same time window, all from outside the solar system. This coincides with the beginning of the Pleistocene ice ages. Voyager 1 and Voyager 2 are sending back data from the heliosphere's edge right now, but they're moving in different directions than the solar system's overall trajectory through the galaxy. They're telling us about where we've been, not where we're going. The local bubble, the larger cavity of hot, thin gas we've been traveling through for millions of years, has walls. Dense walls. Our trajectory through those walls and what lies beyond them is the long-term variable that determines whether the heliosphere holds or collapses, and we have no map. We're driving blind, have been the whole time. Scientists scanned over 56,000 sun-like stars. Same type, same class. Stars that, for all intents and purposes, are our sun's statistical twins. They found nearly 3,000 superflare events. These aren't normal flares. They release 10 to 10,000 times more energy than the largest solar flare ever recorded in human history. And the frequency on stars just like ours is roughly once every 2 to 3,000 years for flares 100 times stronger than anything we've ever seen. Some researchers argue the sun's slow rotation makes super flares unlikely on our particular star. But the tree ring record shows that Miyake events, massive radiation spikes with no known solar precedent, have already hit Earth. Multiple times. The isotope data is in the wood. It happened. The stellar survey data is rock solid. It's Kepler mission science. Thousands of observations across thousands of stars. Where the debate lives is whether our specific sun follows the same rules as its twins, or whether it's somehow special. That's the question. Not, can a star like ours do this? We know it can. We've watched 3,000 of them do it. The question is whether our star is the exception. And that's a bet on exceptionalism, not physics. Here's the thing about lists like this. You watch them expecting 10 separate problems, 10 isolated dangers, but they're not isolated. A coronal hole amplifies a solar storm. A weakened magnetic field multiplies everything. A solar super flare hits different when your shield is already at 91% and dropping. The interstellar medium shifts, the heliosphere contracts, and suddenly, every solar event reaches deeper. These aren't 10 threats. They're 10 variables in the same equation, and some of them are changing right now. The supermassive black hole at the center of the Milky Way is called Sagittarius A star, 4 million times the mass of the Sun, 26,000 light years away, and right now it's quiet. It wasn't always. X-ray echoes detected by the Canberra Observatory show that just a few hundred years ago, a blink cosmically, Sagittarius A star was millions of times brighter than it is today. Something woke it up, it flared, and it went back to sleep. And then there are the Fermi bubbles, discovered in 2010. 2 colossal lobes of gamma-ray emitting gas extending 25,000 light-years above and below the center of the galaxy. Something at the galactic core released enough energy to inflate structures larger than the distance between us and the core itself, sometime in the last few million years. The Fermi bubbles are confirmed. The X-ray echoes are confirmed. What we can model but can't precisely quantify yet is what a reactivation would mean for us. If Sagittarius A star swallows another gas cloud or tears apart an unlucky star, the resulting burst of cosmic rays would wash outward across the galaxy. We're 26,000 light-years away, but light-years aren't walls. They're just distance, and radiation is patient. The center of the galaxy has a documented history of violence. We live in range. In 2007, an astronomer named Duncan Lorimer was digging through old data from a radio telescope in Australia when he found something that shouldn't exist. A single burst of radio energy lasting a few milliseconds. In that sliver of time, it released as much energy as the sun produces in an entire year. Nobody knew what it was. Since then, over 800 of these bursts have been cataloged. Some repeat. Most fire once and never again. The first repeating one was traced to a dwarf galaxy 3 billion light-years away. They are, without exaggeration, the most mysterious recurring phenomenon in modern astrophysics. Then, in 2020, everything changed. A fast radio burst was detected coming from inside our own galaxy. The source was a magnetar, a type of neutron star with an insane magnetic field. So, mystery solved. Magnetars make fast radio bursts, except they don't all fit. The energy levels, the repetition patterns, the environments where many of these bursts originate, they don't match magnetar models. Proposed alternatives range from collapsing exotic stars to cosmic string interactions. Some of the explanations are barely distinguishable from science fiction. And those are the ones published in journals. The phenomenon is real. The galactic source is confirmed. The energy levels are measured and enormous. What's speculative is this. If an F-NRB class energy release happened within a few hundred light years, directed rather than spread evenly in all directions, it would arrive as an electromagnetic pulse strong enough to devastate electronics across an entire hemisphere. We've confirmed at least one source inside the Milky Way. We don't know how many more exist or how close the nearest undetected one is. Something out there is screaming in radio frequencies milliseconds at a time with the energy output of a star. We found out 17 years ago. We still don't know what most of them are. You're not waiting for these. That's the thing people get wrong about cosmic threats. You imagine a warning, a countdown, a moment where someone tells you to look up. But iron-60, an isotope that doesn't form on Earth, is falling on Antarctic snow right now. Right now. Debris from a nearby supernova that exploded millions of years ago, still raining down because the expanding shell is still passing through our neighborhood. The question was never, could it happen? It's which one are we inside of right now?